Right. So first I want to discuss the description of the Cantor set. This problem will be important for several reasons. We will see. But first, my first question is, can anybody quickly review the definition of the Cantor set in the way I said, or in any other way if you have read more or thought? So, right. Okay. So basically, I can translate that as the intersection of Cn. One second, someone is joining. Okay, Rishabh is joining today. Yes. Okay. So Rishabh, do you know about the Cantor set? Do you know the definition? Okay, okay, good then. Yeah. So I had asked a question in that. It's a very fundamental question for several reasons. So today we're going to discuss that. Okay. So today I'm just defining the Cantor set, not defining, but just translating what Adish said as the intersection of these CNs. N intake from 0 to infinity. Okay. Where, yeah, now Cn, how do I define Cn? Do I want to define it precisely, or I can just say that you take Cn minus 1 and 1 minute, remove the, so I'm just defining it recursively. I don't want to define it precisely. I think I'll have a, with computationally it will just involve some, yeah. Remove the middle thirds of the intervals in Cn. This is just an alternate recursive way to think about it. Okay, same thing. 0 to 1. Yeah, so if anyone has tried to give a description, has anyone successfully done that? Or has anyone done anything? And then we further subdivide it. So this. Or maybe there's no need to cross it, right? It's understood. It's on there. And so on. And what we get finally, you can say limit, but it's better to say intersection because these are not numbers, they are intervals. Yeah. So what could be a good description? You know, like you can say that defining the Cantor set in the set builder form, maybe. Or yeah, kind of give a property which describes it. Where I can say good description, or I can say closed description, not recursive, a direct description. Like what numbers, the numbers that are remaining, you know, how would they look like? Do they have any specific property? Yes, yes. So the numbers that are left finally, or the numbers in this set C, you know, do they have any specific property with respect to base 3? Let me say that. So can C be described? Certainly you guys know that the answer lies somewhere in base 3, right? Can C be described well, or can C be described in base 3? I should say, explicitly described in base 3. So first question is, does everybody get the intuition why we are focusing on base 3? I had said this roughly the last time, but if anyone is surprised, then you can say. Yes, 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 yeah. Sorry, example of? In base 3, right, exactly. Yes, right. So given a quantity X, so just writing in base 3. Yes, I mean, the decimals should be 0, 1, or 2. I mean, the digits should be 0, 1, or 2, yeah. But first, let's get the idea of what is going on. Okay. So when we take a real number X, we usually write it in base 10, right? Which means that let's assume X is between 0 and 1. So if X is between 0 and 1, then how do we write it? Let's say 1, 2, 3, 4, 5. What does it mean? It means that it's 1 by 10 plus 2 by 10 square plus 3 by 10 cube and so on. This is what this means. But this basically means that the weights that are available to you are 1 by 10, 1 by 10 square, 1 by 10 cube, 1 by 10 to the power 4, 1 by 10 to the power 5. And using these weights, using some multiples of these weights, you want to break the number, you want to describe the number. You want to describe the number using these weights. Okay. Now, if you think about that, then you can describe a number X. You don't have to use these weights, right? So this is if we use weights of the form 1 by 10, 1 by 10 square, and so on. Okay. So this is like giving a coordinate to a number, a quantity. A number is just a quantity, right? To represent it, basically to give a coordinate to it. This is like giving a coordinate, just like given a point in the plane, we give it a coordinate. If you want to give a rectangular coordinate, then if you want to define it in terms of distance from the origin and angle, then you get a different unique representation, right? It's just about giving a number some kind of a coordinate, depending on your convenience, okay? Right, and all this will be useful much later in vector spaces, spaces, everywhere. Okay, this is basically the game is to give the right kind of coordinates. But then we don't have to use these weights. Then the question is, what if we use weights like 1 by 3, 1 by 3 square, 1 by 3 cube, and so on? Can we still write any number X uniquely? Can X be written uniquely using 1 by 3, 1 by 3 square? This is a fundamental question. Giving coordinates is everything. This is a question. Let's try to answer this question. Okay, so the answer is yes. So now the next question is how? I'm not asking what is the answer. I'm just asking what is the procedure? There are several procedures. Maybe you can say anyone you can think, anyone you can think. Even this year's ISI BMath. First question was like that, right? Any real number can be written like something like that. It depends on paper, something like that, yeah. And all of them have the same method, but let's discuss this. I have discussed the other ones earlier in earlier videos, but we'll discuss this. But this is much simpler, actually, much more. How can you write X using these weights? These coordinates. Yes, just a different coordinate. So meanwhile, you think, I'll draw a diagram. Yes, that's what I was going to draw. Yes. Right. So you have this interval which is divided into 10 parts. Okay. I'm not labeling everything, you can understand roughly. So if you pick this particular number, okay, then it's just a process of zooming out over and over again. If you pick this number X and its first decimal position is 1, then where does this number lie up to the precision that we are given now? Up to the precision given now, where does X lie? In which box? In between which of the two sticks? In the first box. Are you sure it lies in the first box, or you mean this one? Absolutely, yeah. It's because it's bigger, right? So then you can understand, right? So then it is, so any number which has 1 as the first digit, it means that it lies in this box. So how should we go forward? We can just and right. And also any number in this, its first decimal has to be 1. And now you just repeat the process. So you magnify this, or do I need to do that? Yeah, we can just, let's just actually do it here only. So that, yes, we can use the same diagram, right? But let me just, yeah. In this, I just pretend that I'm dividing it again. Let's actually do it like this. And then because it's a 2, it lies in this one, in the third one. So you guys understand, right? This is how it is. As simple as that. This is how it goes. And is it clear why it's in the, because it's 1 by 10, and then this is 1 by, it's 2 by 10. So X is obviously between 1 by 10 and 2 by 10. But then you can say it in many ways, but yeah, X is bigger than 1 by 10 plus 2 by 10 and less than, 10 square. And 3 by 10 square. Right? This is what it means. This is what 0.12 means, right? And this stick, this basically represents 1 by 10 plus 1 by 10 square, right? That's it, that you understand. Okay. Any questions? So it's just a way to go precisely down. And after this, it will just lie in the very first, uh, demarcation after the fifth step in the sixth step. Okay. Mm. Mm. Yes, right. No, but when you're writing it in base 3, yeah, you can get some other point also, right? Mm. Mm-hmm. For the same number, right? Exactly, right. But if I have to say it in a, I mean, basically, yeah. So if I have to say it in a slightly different way, you basically just apply a greedy algorithm. It is the same thing, but this saying it like this makes it combinatorial and it makes it more generally applicable. If there are factorials and whatnot. Okay, meaning that you basically take away. So you're trying to write x using these pieces, right? And obviously, you're not allowed to have more than 2 copies of any piece. See, that's an important condition. You're not allowed to take more than 2 copies of any piece when you're writing it in base 3. So you just say that if 1 minute. So the way to say it would be, you just take, if x is between I by 3 to the I by 3, 1 second. So it's less than no. So there's nothing to be confused about. Once again. Yeah. Yes. So you can say that if x is between I by 3 and I plus 1 by 3, right? So you basically try to find the largest. So you can say it like this. So you basically use as many copies of 1 by 3 as you can. Okay. So pick the largest I such that x by this such that this is positive. Largest I. Okay. So maybe I should write like this. Pick largest I such that this is positive. Okay. And then you repeat the same thing for x minus 1 by 3, right? 3 square. Yes. But after this, after you do this. Yeah. So after this, then you take this as your. Yes, right. Yeah. So then basically you take this as your x1, right? And then you pick the largest I such that this is positive. Right. And then you call this x2, and then you do repeat the same thing. Okay, so it's basically, I mean, x is a quantity here. You're picking as many copies of x by 3, sorry, as many copies of 1 by 3 as you can. Okay, and then the remain, so this is like maybe 2 by 3 you picked, removed from x, and then you have the remaining number. In that you pick as many copies of 1 by 3 square. Okay, meaning 0, 1 or 2 copies, and then you remove that quantity and then you continue. Is this okay? Yeah, is it okay with everyone? This is the, I'm saying it a little loosely, but now your job is to prove that this gives a unique representation. It will, yeah, you try to see. Sometimes it will not. So, but there will be at most 2 representations. Prove that this process gives a unique, with some exceptions, representation. Yeah. So what I'm saying is that you have to show that every number can be written in this way, because we have yet not shown that this process terminates or this process converges. Is that right? Yeah. So you have to show that the process converges, which means you have to show that for any epsilon greater than 0, there is an I such that after the ith step, this difference between becomes less than epsilon. Is that right? In this process, right? You have to show that these things happen. Okay, so try to do this. Like do this because this is a good exercise. Simple, but okay. Yeah. So that should clear the thing. One minute. I mean, the convergence is there. You have to do it. That is not done yet. Okay. Yeah, so I can remove this. So this is all about giving coordinates. And then do the following question. So this is another question, related question. This is important. It will involve some convergence and some combinatorics both. Okay. So let's see. So show that given x in reals, okay, show that given x in real, there exists distinct naturals. And some of you may have done this. I had done this earlier in some earlier class, but not in full generality. We have done it for rationals, I think. Distinct, but now that we know some analysis, we can do this. And I'll try. Distinct naturals n1, yeah, n1 less than n2 less than n3, and so on, such that x is equal to, this is pretty amazing result actually. In some sense, looks very amazing. Try to do it for rationals first, maybe, and then this is a, when this was some context or some contest, but that it was only for rationals, and that is purely combinatorial. But then it gets analytic when you do it for reals. So try it. It can also be framed as saying that something is dense in something, but just writing it like this. So try it, and then we can come to the, just note it, then we can come to this. The Cantor set. So now you get an idea. Now the Cantor set also, like we did in base 10, we were picking from some grid. Cantor set is also picking, right? So if you write an element which survives, it means that it is in all of these. It's in this, obviously, then it's in this maybe, then it's in this. It's what will be the decimal, what will be the base 3 representation of that? Meaning, basically you can think of x is between powers of 3 and something like that. Take a time, this is, yeah, this thing. Yeah, no, these two are for homework, not because you'll have to spend some time thinking about it. Then first write the process clearly, maybe do some examples on your own, try to prove these things. Okay, this will take some time maybe. So right now we are doing the Cantor set. Okay. See, the first decimal place is decided at the first step, right? So if x is, this is just the novelty of the question, type of question maybe, but it's in fact not difficult. If x is in C and you're writing x using powers of 3, so and so on, right? Something like this. It may not terminate, but what can you say about I1? You can certainly say something. So yeah, so you see, let's say, let's go to base 10 again. Okay. If I am doing this, and then I am in the next step, I am only taking numbers between 0 and 1 by 10. And then what can you say about the first decimal place of the numbers here? Inside the yellow box, the numbers. Yeah, so you can say that the first decimal place is 0. Right? That's exactly what it means. So basically, the decimals are taught as usually discussed in a very, just a methodical, yeah. But it is basically, you understand now. Okay? The decimal is just a convenient way to write it. Yeah. So now, in that sense, what can you say about I1? So the number that you're looking at is either in this, or in between 2 by 3 and 1. So in that case, what can you say about I1? So x is between 1 by 3 and 0, but this is not entirely, this is incomplete. Or x is between 2 by 3 and 1. because both the possibilities are there. I mean, in the sense, if I'm asking this, yeah, to both. So how does that translate to I1? So if I, for a second, if you remove the 1 by 3 and you just consider this, what can you say about the I1 here? This implies that I1 is 0. Right? Because the first, you can think of it in many ways. The first chunk that you're trying to take away, the first chunk, I mean, how many 1 by 3s can be taken away from X? No 1 by 3s, so 0. You can think of it in many ways. So for a second, let's forget about this 1 by 3. I mean, even if you take it, it's not a problem, but yeah. But let's for a second just keep this. You can take it, it's okay, but it becomes a little complicated. So this, and what about this? What about when the X is between? Absolutely. So does everybody see this? Does everybody understand the weights thing and so on? This is just like in base 10, right? It's in the third interval, it's in the last one, so it will be between 2 by 3 and 1, which means, yeah, the second decimal will be 2. So the second decimal is either 1 or 2. Sorry, either 0 or 2. I mean, certainly these two are possible. 1 is also possible, but these two are certainly possible, at least. And all numbers which have this property are there in C. Is that correct? Is that correct? Yeah. So all numbers with I1 equal to 0 or 2 are in C. Or maybe you can just simply think about now what can I2 be? Yes, I is either 0 or 2. It is not 1. I mean, all numbers with, I mean, these numbers are not there. So certainly this is possible. 0 or 2 is possible, right? Yeah. Uh, mm, yeah. Okay. That's right. What can you say about I2 then? Yeah, that also you can just extend. As Raghav said, you can just extend it. I2 equals to 0 or 2. If you just forget this boundary case for a second, if you we're just omitting this. Okay. Because once again, you can just take this, right? I mean, those are there. Just by the same reasoning, right? Yes, and you see the same thing will happen, right? Or you can just take 3x and do the same argument. Yeah, just think about. No, but I2 can either be 0 or 2. No, 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 no. But you see, so if I take something here in this ping box, then that x would look like what? That x would look like 0 by 3 plus 2 by 3 square. Is that right? But if I take something in this, then that would look like 2 by 3. This green, the items in this green would look like, one second, I just plug. Right. So that's what happens. Just that's what same thing that happens in the decimals. That's right. Yeah. Okay. So just think about this. Okay. Think about this more. Right. The second decimal place and so on. So basically you see any number with ik equal to 0 or 2 is in certainly in C. Is certainly in the Cantor set. Now this is again something that you can prove. So the way to do it, let's take an example. I mean, you can do by induction, but let's take an example. If you take something like, let's say 0, 2, 0, 0. So I mean in base 3. I can also write it using powers. Let me do both of them. Then you have 2, 2, 0, 2, and let's say it doesn't finish. That's not a problem. This basically means 2 by 3 square and 0 by, you understand? And then cube, third, fourth, fifth. So this is 2 by 3 to the power 5 and 2 by 3 to the power 6 and then 2 by 3 to the power 8, right? How can you get this number? Can anybody quickly describe how can you find it in the Cantor set? Like what boxes you have to jump? How do you have to choose how to go down? No, this entire number. Yeah. Mm-hmm. Yes. So choose the first box. In that, yeah. So then the rest of it we can forget. Yeah. Mm-hmm. Yes, because of the 0 and so on and so on. Okay, so this is a thing. I've just said through an example. You have to think this through and do. Otherwise, it will take a long time to explain. Okay, so yeah, but roughly you get. Okay, so certainly we are able to say that all numbers with 0 or 2 in the decimal. I mean, you can just say not decimal base 3, but yeah, any sequence with length with any sequence made up of zeros and twos is there in the Cantor set. Okay. So what does this say about the Cantor set? Just say so. C is basically the, yeah, just a yeah, exactly. Infinite sequence of zeros and twos. Infinite sequence of zeros and twos. That's all it is. In base 3, but it's a unique interpretation, right? Every sequence of zeros and two has a unique interpretation. Now, I did omit one thing. So, what happens if you take? Let me say that. So this is mostly enough for what can be expected in questions that you will encounter. And this also, let me just say, what about, so I did skip something. So let me say that this thing, what about the number that lies here? Yeah, this number is 1/3, right? Now 1/3 is certainly in the Cantor set, right? Because this 1/3 is going to survive. I mean, these are the obvious elements. These are the obvious elements, right? The endpoints. Is that right? Yeah. Right. This is the obvious element is there in the Cantor set. It will definitely survive, right? You subdivide, but you're always going to take this, and then you'll always take this endpoint. Can this number be written using only zeros and twos? So if you write 1/3, I mean, obviously one way to write 1/3 in base 3 is just 1/3. Okay. So in that sense, it is just, can it be written in a different way using zeros and twos? So what will that be? No. How can that be equal to 1/3? Right. So if you ask yourself like this, how can this be 1/3? Okay. Yeah. So this cannot be 1/3, right? Yes. Yeah. Just logically, right. Right. So before, even if you go to the representation and you can check it, but 0.22222. I mean, this is what it should be. Base 3, sorry, base 3. This is base 3. I mean, these two things are the same things. You can do it in several ways. I mean, you can just write the geometry progression and check the summation. Yeah, so it's this is, and this, by analogy, right? Basically, this number is the limit of numbers. Yeah, you understand. One second. Yes. Yeah. So the way it converges, 1 minute, let me just think. So yeah, you pick a number in this, and then you take 0. So I'm just 0 and then 0.02, 0.022. If you just draw these, if you just point these numbers, you will see that they will actually converge to, pictorially converge to 1/3. If you write their meanings in base 3. Yeah, that's right. But I'm just saying that even if you write this integral, integral in what sense? Uh, I don't know. Yeah, maybe. Okay, maybe. Okay. Anyways, this is sufficient now. Yeah. So now the point is that this actually implies that the Cantor set is uncountable. Because I don't know, you might be knowing that the real numbers are uncountable. That's not, we're not going to discuss that rigorously, but the real numbers are uncountable, right? So yes, they don't have a bijection with n. And simple reasons can be given, but that's not in our, if we do that, then it will go in a different direction. So yeah, so basically real numbers can be written in terms of zeros and ones, and sequence of zeros and ones is uncountable, right? That's what the real numbers between 0 and 1 is. And that is a sequence of zeros and ones, and that is uncountable. So if that is uncountable, then for the same reason, sequence of zeros and twos should also be uncountable, right? So C is uncountable. But we had seen that the area or the length of C is 0, but C is uncountable. Okay, so in that sense of size, it's very big, but in the sense of length, it's very small. Okay, so it's 0. So you can make out what you want to make out of that. Okay, but basically these two are very different notions. Okay. But we just did it as an exercise in basis. So you can, but basically you understand that choosing a certain kind of coordinate or certain kind of basis will depend on the process that you're doing. The coordinate that you choose should reveal something, should reveal some pattern in the kind of things you're trying to represent or the kind of process that you're doing. You should choose a useful basis so that the representation gives you some pattern, right? If you try to define the Cantor set in terms of base 10, if you choose the coordinates as 1 by 10, 1 by 10 square, then there is no good description, right? There you cannot say anything about the weights. You cannot say anything familiar, like, only zeros and twos, or this many zeros, this many twos, something combinatorial, something close, something in a sentence, you cannot say. But once you change the coordinate system, or changing the coordinate system is just changing your perspective, right? Right? Then it becomes easily describable. This is a very surprising thing, strange thing, but this is what mathematics we do throughout. I mean, this is basically choosing the right coordinates for something, or choosing the right model in general. Okay. So yeah, so you have to, given a situation, you have to guess first what's the right basis to take. It could be number basis, it could be polynomial basis. For now, maybe that will solve the problem, but you have to first be comfortable with this basis thing. Okay, I have discussed this in earlier classes also in some unique ways, so maybe I can share that later. Okay, so that was all about Cantor set. Let's move forward. Any questions? Okay, yeah, so today I just have to end on time, so let me go to the next thing. Yeah, the next thing was another important problem, so which I had asked, and this is again useful in the theory of integration. Yeah, this will lead to a very important question which we'll answer. So the question first was that find f from R to R. F is unbounded. But this area under F, you can just take 0 to infinity or whatever, doesn't matter. So first let's not do 0, let's do a simpler one. So this is a problem that we kind of went to this problem through other simpler problems. Okay, let's think about that. So fx is equal to, no, but the problem with this kind of thing is then showing that f is integrable becomes a theoretically challenging question maybe. I had also put a condition continuous. This kind of function won't work, right? Because this is not a continuous function, not continuous. Can somebody give a reason why this is not continuous? I mean, yeah. Right. And if that number is not 0, then it is not continuous at that point. Right. So this is continuous nowhere almost. Wait. Or yeah, no, that is certainly true. Let's see. One second. Yeah. So I'll get to, no, 1 by x is not, it's not, area is not 1. But one, yeah, maybe that's correct. I'll come there. But if I take a sequence of rationals, so let's just do this carefully. Let's take a point x naught. Then you take a sequence of rationals tending to x naught. And the function values will tend to this. This will be the function values. If you take a sequence of irrationals, tending to x naught, then this will go to 0. Okay. And these two are not different. These two are going to be always going to be different things for any x not equal to 0, right? If x naught is not 0, then these two are different, right? This is equal to x naught cube, and this is equal to 0. Okay. So these two are different things. And so, but then we have proved that this is apart from 0, it is not continuous anywhere. Is that right? Yeah. At any point, it is not continuous. Not even at irrationals or rationals, not continuous, right? So this will in fact not even be integrable. We don't even know what that means, right? Yeah, it will not be integrable. Not yet. Yeah, but we will soon be able to say that rigorously. Yeah, integrable is very, yeah, still it's hard to say because there are non-continuous functions which can be integrable, but yes, yeah, those things are certainly, that is certainly integrable. Yeah, if you take a straight line and if you remove this point, certainly that's integrable. So just 1 minute, just a little confused about something. Just give me 1 minute. Theoretically, I am getting that it is integrable, but I mean, and then some, so intuition is telling me that it is integrable because rationals are, I'm getting confused about something very fundamental. So intuition is telling me that this should be integrable because rationals are most of it, and irrationals can be covered with intervals which are very, very small. And so the total, that weighted sum of intervals and values, that should be 0. That should be made to, can be made to tend to 0. No, wait. Yeah, but maybe if you choose the wrong intervals, then it will not. Yeah, but then there is the theory tells that if it's non-continuous only on a small set. Yes, I got it. Yeah. So I'll discuss that later. That was just for my own sanity. Sanity just as I was I will say that later, definitely. Yeah, because there are too many bad points. You can't help it. Yeah, by making their effect small. Okay. Anyways, I'll say that. Yeah. So this is not even integrable. We'll prove that later. Okay. It's a very interesting concept. So this problem still stands. So yeah, so someone said 1 by x. 1 by x is certainly unbounded, but it is not defined on all reals. We want a function that's defined on all reals. But it is still not, I don't think the integral is finite, right? Yeah, integral is not yet, still not finite. So that's, yeah, integral is not finite. You can check that even by calculations. So remember, we were doing this question. We were coming at this question from length of rationals. Right? We kind of took the rationals, we surrounded every rational with small and small intervals. Remember? And we proved that the length of naturals, okay, we did, and rationals you can do similarly because you can list them. But the whole idea was that there were infinitely many numbers with infinitely small sum, right? There were infinitely many numbers, and the numbers were becoming infinitely small, but even the sum was infinitely small, right? That was the that was the maybe a new thing, okay? Second order smallness. Infinitely many numbers, and this is the idea, with infinitely small sum. Right? What do you mean by infinitely small sum? I mean, any epsilon, you can produce such infinitely many numbers whose sum. And that was we know now this trick. This is a fundamental thing. Once you can make something finite, you can make it as small as you want. Can you extend this idea to functions? Can you create a function from here? Well, you don't even need so much. You just need to make it one. You need to make the sum one. So you need to find a function whose sum is one. Area is one. No, but then see, yeah, that's right. That is the idea. But this is not a function on real. This is a function on the naturals, kind of, right? We want to convert it to a function. That's why it's a slightly harder question, if you may think like that. So this was like x1, x2. So this is a function on the naturals, and that is one. Now you have to extend. Yes, yes. Finite integral is the, yeah. E to the power. Okay, okay, yeah, that might. Uh, uh E to the power. No, but the e to the power, if you take minus, then it's not unbounded, right? It's even worse. It's goes to zero, but it's not unbounded also. So basically, okay, if you think about this, there's a new idea. And this question, I just actually ended up making this question up. Obviously, this question will be there somewhere. Discussing with some friend, I remember long time back. Discussing. But that's not unbound. Okay, yeah, that might work. That might work. Oh, well, yeah, that's a good example. And I remember, my friend actually gave some example like this. I made some very geometric example, and she just says, friend thing. This right? Is this integral finite? Can anybody check? So this is certainly. So first of all, okay, but is this unbounded? I might be. Yeah. Is this unbounded? No, right? It is always negative. So this is negative. So it's always less than 1. But there was some example like this. I don't remember. 2 by pi, 2 by pi, okay, into tan inverse x, okay. And then you take the integral. Okay, first of all, is this unbounded? Yes. No, but the problem with this function, yes, so certainly, yeah, I'm just not functioning, right? Yeah. Yeah, this is not unbounded. Its domain is, the range is not unbounded, right? It's between, not unbounded. Yeah, sorry, that doesn't work. Yeah, it's not unbounded. If you just convert this to the actual geometry, kind of, then it might work. I don't know. Yeah, but there is some new idea, I think. Or something like E, something with E might also work. Let's think. Does E to the power 1 by X work? So what is the integral of this? No, it doesn't work. No, this will not work. It's because at Z, it is not defined. Yeah, but if you define it, yeah, but how would you define it at 0? That's yeah. Yeah, it goes to infinity. No, but then you see, yeah, it does go to infinity. But if you still insist that you define it like this when x is not 0, and you define it to be 0 when x is 0, then can we check what happens? Yeah, this will not work. Yeah. So what will the integral be? Some minus x square, right? How will that change anything? That will not change anything. No. But then it will come at 1, right? The same problem will come at somewhere. I think, yeah. This. uh, okay. Okay. But then it's not unbounded. Yeah. Yeah. Yeah, but then that's cheating. You have to you have to whatever you consider it has to be unbounded in that. Otherwise, what is yeah. So then if you take this, then when x goes to 0, yeah, this doesn't even converge. That is a problem. This anyways, yeah, this e to the power minus x, e to the power minus x is okay, e to the power minus x. But this is less than 1 between 0 to infinity. No, I mean, but okay, then let me just make it r 0 to infinity. And so yeah. No, but then e to the power minus x is less than 1, so it's not unbounded. Yeah, because someone I think there was an example like this. Someone had told me once. Just and I don't remember it. Yeah, but I am not even thinking of this. I'm not insisting on this, and I am actually insisting on the geometric thing. Okay, so let me just give you a hint, and you can do this next time. Okay, the idea is that the region, so the so see the idea is see that f becomes unbounded, but you have to make a function which kind of so it does attain big values, but then it comes down again. Okay, and the time for which it has those big values is pretty small. Okay, the time for which the big values are attained is small. Something, right? So it kind of attains this big value, but then comes down quickly. It attains this bigger value, but it comes down even more quickly. Bigger value and then comes down more quickly. Something like this. Okay, that's now you have to think. Yeah, something you can make it spike. Spikes is the natural way to get it. Yeah. Okay. So please think. X cube thing is not, there's no. Yes, yes, right. But then that is not a good function. Yeah. Because it's not integrable. And even to prove it's integrable will be difficult and it's not continuous. So, anyways, yeah. I mean, if you write such an example, then you have to, it becomes theoretically challenging to, yeah. But there is power in those kind of examples because those you can actually prove, you can make it 0, but then it becomes difficult to prove. Okay. So let's do this problem, think about it. So today we didn't do any theory. We didn't kind of move forward in that way, but okay. Yeah, sorry. Okay. So that's it for today. Okay. We will, tomorrow we will not, tomorrow we'll have some graph theory kind of thing. Saturday we will mostly try to do. Okay. Yes. Yeah. So subjective. So where did I get my problems? Where did I practice? Have you looked at Spivak? Spivak calculus? Indi- Those kind of things. Yeah. That's right. Definitions. Yeah. Have you done all the plus two problems in the integration? Try them. Like in that means tomato. Yeah. Yeah. Okay, then let me. Yeah. Mm-hmm. Yes, yes, yes. Yeah, yeah, yeah. He's very good actually. Problems are very good. Yeah.